Hi, this is my presentation on the fundamental theorem of algebra. And our objectives for this lesson are that we can use the fundamental theorem of algebra to determine the number of zeros of polynomial functions, and we'll see some examples like that for polynomials of varying degrees. So a linear polynomial, quadratic, degree of 2, cubic, just so we can see how the fundamental theorem of algebra works when we look at different types of polynomial functions. We'll find rational zeros of polynomial functions. If we need to, in any of our examples, we'll find conjugate pairs of complex zeros, and then if needed, based on what our example is, we may find zeros of polynomials by factoring. So what is the fundamental theorem of algebra? How are we going to use this theorem to be able to determine the number of zeros of polynomial functions? So the fundamental theorem of algebra allows in the complex number system, for every nth degree polynomial function has precisely n zeros, and this was derived by Carl Gauss. And we have seen a similar one like this in our notes from this chapter, but in our textbook, the fundamental theorem of algebra is defined as if f of x is a polynomial of degree n, where n is greater than 0, then f has at least one zero in the complex number system. So that can be confusing for students at times, but the key being that the degree of n, where n must be greater than 0, then f is going to have at least one zero in the complex number system. Looking at this fundamental theorem of algebra, it's going to be important that we revisit the linear factorization theorem as well, because this can be a way that will help us to determine how many zeros we have in a polynomial, and then by looking at the zeros, decide if they're in the complex number system. So we look at our linear factorization theorem. This will allow us to be able to determine our factors, and then from our factors, find our zeros. So in our textbook, the linear factorization theorem is if f of x is a polynomial of degree n, where again, n has to be greater than 0, then f of x has precisely n linear factors. And a sub n will be your leading coefficient. And then C1, C2, all the way through Cn are any of your complex numbers, and with those also being their factors as well. So let's take a look at our first example before we get into some where we would expect our students to kind of look at. So for example, if we have a first degree polynomial, f of x, where f of x is x minus 2, then it has exactly one zero, x equals 2. And again, in this example, the 0, x equals 2, is a rational zero, so it is in the complex number system. Looking at our second example, let's look at a polynomial, a second degree polynomial. So we're going to look at something called multiplicity here. So if f of x is the same as x squared minus 6x plus 9, it would be important to use our factorization theorem to factor this polynomial so that we can determine our factors and then ultimately determine our zeros. So our factors, this factors to give us x minus 3 times x minus 3, and if we were to solve these, set these each equal to 0, we determine that our zeros are x equals 3 and then ultimately x equals 3 again. This is known as a repeated zero. Our textbook refers to it as a repeated zero. Oftentimes we tell students to refer to this as multiplicity of 2. But again, we see that it has a rational zero, and both of these would be falling in the complex number system. So again, a degree of 2, we notice that we have two zeros. Ultimately, they are the same zero with multiplicity 2 or a repeated zero. Looking at our next polynomial, for example, where we would have a third degree polynomial. So the third degree polynomial function, f of x is the same as x to the third plus 4x. So again, applying our linear factorization theorem, we have it factor to x times x squared plus 4. Now, we can expand this a little bit to factor, and now we have two conjugate pairs of our complex zeros. So x squared plus 4 factors to x minus 2i and x plus 2i. So x minus 2i times x plus 2i. So here's an example of our conjugate pairs of complex zeros. So if we were to then go further, we see that this third degree polynomial function has exactly 3 zeros, x equals 0, x equals 2i, and then x equals negative 2i. So in this example, we have one rational zero and two complex zeros. So we still have 3 zeros, just one happens to be in the rational numbers while the other two fall in the complex zeros. So again, still third degree, 3 zeros, x equals 0, and x equals 2i and negative 2i, which would be our complex zeros here. All right, so looking at some examples where we would expect students to try these on their own, maybe at the first attempt. So determine the number of zeros of the polynomial function. So we'll start off with an easier example similar to what we saw in the previous examples, x plus 4. Since this polynomial has a degree of 1, it should have exactly 1 0. So to determine that, we set this polynomial function equal to 0, and we find that x equals negative 4. This is a rational zero or a rational root, so therefore this polynomial has one rational root. Now we can determine that, and it makes sense based off the degree of our polynomial being 1. It makes sense that we have one rational root. All right, example 2. Determine the number of zeros of the polynomial function x squared plus 5x minus 6. It would be useful here to use our linear factorization theorem to factor this polynomial. Since it is a degree of 2, we are expecting that it should have exactly 2 zeros. So factoring this polynomial, we factor it to be x plus 6 times x minus 1. And we can set each of these factors equal to 0. And we can find that our zeros then are x equals negative 6 and x equals 1. Both of these zeros are in the rational number system. So both of these zeros are rational numbers, and therefore this polynomial has two rational roots. So we've used our linear factorization theorem, and because we have a degree of 2, we expected that there was going to be 2 zeros, and by factoring we determined that there were 2 zeros and both of our roots were rational. Our third example, so a different one than our previous example because this one has x plus 5 squared, so we have a binomial squared. So again, because the degree of this polynomial, the polynomial has a degree of 2, this should have exactly 2 zeros. Now, it might be helpful to expand this polynomial, this binomial out. So we have x plus 5 times x plus 5. And in this case, we are going to have a repeated root or a multiplicity 2. So x equals negative 5 is a repeated root where the multiplicity is 2. So again, therefore, this polynomial has two rational roots. So let's try a more challenging example. F of x is the same as 1 minus x to the third. So the degree of our polynomial here is degree 3. So we are expecting that there should be exactly 3 zeros. Factoring a cubic using our linear factorization theorem, we have 1 minus x times 1 plus x squared. This linear factor here, we can determine that x equals 1, and it's a rational root. This here, this degree of 2 polynomial, is going to give us some complex roots, and those complex roots are negative 1 minus I square root 3 over 2. That would be our complex root. And then negative 1 plus I square root 3 over 2 is our complex root as well. So therefore, this polynomial has one rational root and two complex roots, but we were able to tell initially that it was going to have a polynomial with 3 zeros, and in this case it does. Just one of the roots are complex, and the one of the roots are rational and the other two are complex. So just to kind of summarize here and keeping track of the fundamental theorem of algebra, I think the big key to make sure that we understand is that the fundamental theorem of algebra and our linear factorization theorem only tell us that the zeros or factors of a polynomial exist. They do not tell us how to find them. So we have seen a couple of examples where we could simply factor, or we could expand and then factor. And we even saw one example where we might need to have performed the quadratic formula. But in all 4 examples that we looked at, we could identify how many zeros we had and that they did exist, and then we had to then ultimately take the next step into determining how to find them. So this was my presentation on the fundamental theorem of algebra.